Hi everyone, in this video I'm going to introduce yet another term. So this is another major building block we're going to use to build some more theory. I promise we'll get to the more interesting stuff soon, but I'm going to introduce the concept of nested refinement, which isn't standard terminology, but I don't know what the precise term is. There's probably other terms out there, but I'll call it a nested refinement. So I'm just going to say, because all our assumptions so far has been kind of repetitive, so throughout I'm just going to fix f to be a function defined on an interval I, closed interval I equals a to b, and script p to be the set of all partitions of I. So we're going to assume, if you wanted to, you could write all these out at the top of each of these things that we're going to discuss in this video. So I'm going to take a sequence of partitions, and I'm going to say that that sequence is what I'm going to call a nested refinement, to be simply, if you give me an n, the next part of the sequence is a refinement of the previous. So as you can imagine, how we're going to use this definition is in refining the mesh in a sequence that converges to what we call the Riemann integral. So the main thing we're going to prove in this video is another lemma. And basically what this lemma says is, if you give me a sequence Pn, I don't know if it's a nested refinement, Qn, I don't know if it's a nested refinement. No assumptions on either of these sequences of partitions, right? So they're contained in P, such that the this sequence U of Fpn decreases to the upper integral, and the Qn increases to the lower integral. You can pause the video here if you're not entirely convinced. Why can I write decreases? So here, the down arrow, here down to the right means it's both converging, but it's also decreasing. And similarly, this one is converging, but also increasing. Why can I write this? So you can pause the video in here to think about it a bit. The reason is because this upper integral is an infimum, so we know that there's a sequence that decreases, and this is a supremum over a set. So we can always find a sequence that increases to its limit. And so the crux of this is, I have these two different partitions, but it would be nice if I could have one partition that's one sequence of partitions that's common to both, and such that it's a nested refinement, because it's a nice object to work with. So that is exactly what we're going to show. Is if you give me these Pn and Qn, I can always construct a new sequence, Rn, that is a nested refinement, that has this nice property, and such that Rn is a refinement of both the Pn and the Qn's, and finally, that we preserve this property here, that the upper integral decreases to the lower Riemann integral, or Darboux integral here, and then similarly for the lower one. So let's go ahead and prove this. I actually prefer the orange here, so I'm going to switch up on you guys. So to prove this, you can think about it's a very simple construction. You can think about this a little bit and pause and see if you can think what we're going to do here. So continuing here, sorry, I think it's simplest to write it like this. There's a few different ways you can write this, but I'm going to do it this way. So first I'm going to say R1 is this, and now that Rn, and then for all n greater than or equal to 2, I'm going to say Rn is, so Rn minus 1 is now defined, and then I'm just going to union it with Q, oh, not Q2, Qn union Pn. And that's the construction. So now we need to show that it's a nested refinement. It's a refinement of both Pn and Qn. So I'm just going to say clearly Rn is a refinement of, well, we can actually just do this concisely. So since Pn is contained in Rn, Rn is a refinement. And that Qn is contained in Rn. Rn is a refinement of Pn and Qn. Similarly, since Rn minus 1 is contained in Rn for all n, Rn is a nested refinement. Okay, so we've now shown that Rn is a nested refinement. And that at each level we refine Pn and Qn. So now we have to show these. So what are we going to do? Well, I'm going to invoke our previous video. So from the previous video's lemma, for each n, we have that U of f, so it's an infimum, right? Rn is a partition. So since it's the infimum, we have that. But also, since Rn is a refinement of Pn, so that's the previous video, and Rn refines Pn. I'm just using that result that we showed. So, if we take the limit on all sides, we have that U of f is less than or equal to the limit as n goes to infinity and then this limit is U of f by assumption. So that tells us that the limit as n goes to infinity of U of f and Rn is U of f. We're not quite done. Forgot to mention this. So we need to show it actually decreases, but this is relatively simple. So again, from the previous video, and from definition of nested dissection, or not nested dissection. Nested dissection is a completely different thing. That's a numerical analysis thing. So from nested refinement, we have that U of f Rn plus 1 is U of f Rn. So again, we're just applying that same lemma. And so just to be explicit, so U of f Rn as a sequence decreases to U of f like we wanted. And similarly, and I'll leave these details to you, similarly, that increases to the lower interval. And that's it. So the main takeaway of this result is that we can get a very nice, we can always assume from now on, okay? Because we're going to take these sequences because they're defined as infima and suprema. We can assume without loss of generality. So from here on out, we can assume without loss of generality that the Pn is equal to the Qn and that it's a nested refinement, which is a nice tool to have because we don't have to go ahead and, we have a different sequence here with the upper one and we have another one here and we don't really know how they relate to each other in refinement. No, we can take a common sequence for both of them that is a nested refinement and preserves this limit property. That's the main takeaway here. Thank you guys for watching.